Alright, hello. In this video we're going to introduce and look at linear approximation. So this is an application using the derivative. Somehow, let's see how it works. So the idea behind this, imagine that we have a differentiable function f, so the curve here in blue, and we want to look at the tangent line to the graph of f at a specified point. So it looks like in this case we're looking at it about x equals 1, and we've got our tangent line there. So the idea is, as I zoom in, the tangent line and the original curve are going to become more difficult to distinguish. So zoom in a little bit there, zoom in, zoom in, zoom in, and around this area, you can hardly tell the difference. This is a computer-generated plot. As you might guess, it plotted the tangent line second, so it's kind of overlaying the curve, but you can't tell the difference from one to the other there. So that tangent line for a function, differentiable function f, the tangent line at a is given by this equation. Right? And so for x values near a, that function, the function value is, what this is saying is kind of what we just said in words, it's saying in mathematics notation. The function is approximately equal to the tangent line. That's what that's saying. Here's the tangent line. F is approximately equal to that. So we call this the linear approximation of f at a. It's just the tangent line. And the function whose graph is this tangent line, we have a separate name, a new notation in the book. They call it the linearization. They denote that by a capital L for linearization. So it's just a function, basically a function that is the tangent line. Just another name for it. So the question is, why are we doing this? And the idea is, well, we're making approximations. So why would you make an approximation? Well, you might not know the value of f at a particular value, you might know it at a particular value, but not for a value nearby. So you use the value that you know, and if it's the one that you're trying to find, if that's close, you can use that as an approximation in part of this process. Kind of fumbling my words here, but the idea is we don't know what f is at a certain point, but you know what it is nearby. You can use that with some extra information to get a pretty good estimate of the unknown. So a linear function is really easy to evaluate, relatively speaking, and if x is near a, this can oftentimes be a good enough approximation. But the thing we have to remember is that if we're going to do this process, now there's other approximation techniques you could use, but for this process, we need to have a function f such that we know the function value and the f of x that we want is such that x is near a. Alright, so with that in mind, we can look at an example of something like the following. So I've got this function, square root function, and what I really want to do is estimate the square root of 3.1. Now, I know, oh jeez, let me pause that for a second. I got a typo here. I'm going to just go ahead. I'll fix it on the slides that you see. We're on such a roll here. We want to use 9.1. Sorry for that mix-up, but I'm going to keep it going here. So I want to estimate square root of 9.1. We certainly can estimate square root of 3.1, but that would be a different process than what we want to do here, what we're trying to illustrate. So the idea is, I know what the square root of 9 is. It equals 3, right? And this is close. Whatever we mean by that, but I think we can agree by some standard, we'll say that this is close to 9. Okay, so let's find the linearization, like we said here. So we want to recall the linearization at 9 would be f of, in this case, f of 9 plus f prime of 9 times x minus 9. So this is the value, this is the thing that we know, the f of 9. We're going to figure out f prime of 9 as well, and that tells us the slope of our tangent line. It tells us how far up we're increasing, or going up or going down, if you think about it graphically, for a given change in x. Okay, so f of 9 is square root of 9, which is 3. And f prime of x is 1/2 x to the negative 1/2, or you might like to write it like this. So f prime of 9 is 1/2 times the square root of 9, which is 1/2 times 3, so 1/6. So we've got everything we need for the linearization. So L of x is f of 9, which was 3, plus f prime of 9, which we said was 1/6, times x minus 9. So that's the linearization. That's the first task we're supposed to do. And we know that for x values near 9, L of x is approximately, which is just the tangent line, is approximately equal to the function. They're exactly the same at 9. So the square root of 3. I gotta fix this slide as well. Sorry for that. Remember we wanted to do square root of 9.1. So the square root of 9.1, which equals f of 9.1, is approximately the same as L of 9.1. And I know that. Let's just plug it in here. So L of 9.1 is 3 plus 1/6 times 9.1 minus 9. And that's just 0.1. And so it would be, if you like, 3 plus 1/60. 1/6 is 0.1666666. So you might say it's 3 plus something like that. And let's just say it's about 0.017. And so that's our L of 9.1, and we know that's approximately equal to f of 9.1, which is the square root of 9.1. So we know that's going to be a little bit bigger than 3, because the square root of 9 is 3. And just think about what this function looks like. That's what we have. So functions, these can maybe get a little bit trickier, but it's not really too much more than this. So you got to get the language down, know what we're talking about, what we mean by linearization and whatnot. But really what we're doing is just using the tangent line to approximate a function. So that's it for this. That was our introduction, and there's not much more to say about that. So we'll leave it there.